Now we're going to take a look at rational inequalities. All right, rational inequalities are going to be very similar to polynomial inequalities with a few differences. Remember, I mentioned that polynomial inequalities, polynomial functions are smooth and continuous. Rational inequalities, or rational functions, I should say, are not. Particularly, they're not continuous. And the places where they lose continuity are at two places: vertical asymptotes and holes. Now the holes are more rare, but they exist. Okay, so rational functions are not continuous at vertical asymptotes and holes. Okay, so those two places. So those are the two places in addition to x-intercepts that we need to test when using a sign chart. We know that anywhere else where the graph is continuous, it can't switch sign from positive to negative or vice versa, except at an x-intercept, okay? But at the discontinuities, we could have a problem. An example, I can prove this, so if I were to look at a vertical asymptote, your rational function can change from positive to negative values at a vertical asymptote, right? So this graph is positive, and then all of a sudden at that intercept, at that asymptote, it changes to negative values, okay? So immediately to the left they're positive, immediately to the right they're negative, or vice versa, you could flip that around. Okay, so vertical asymptotes definitely need to be tested on a sign chart. Also holes. You could, in theory, now this is way more rare, but you could in theory have a function that maybe, let's see, does something like this, and then has something like this, but maybe happens to have a hole right there on the x-axis. That's a possibility, although very rare, okay? And so because that's the case, because you could have a hole where on one side the graph is negative, the other side is positive, or vice versa, we do have to test for holes, okay? So in my instructions here, I'm just going to make a couple tweaks, okay? When I say find the zeros, I need to find all values for the x-intercepts, vertical asymptotes, and holes, all three of those things. But remember, all three of those things occur as zeros of either the numerator or denominator of a rational function, or both in the case of the hole. So I want to find the zeros of the top and bottom, okay, the numerator and denominator. Those will determine for me what the x-intercepts and the vertical asymptotes and the holes are. All right. Then I make a sign chart, and that sign chart must include all of those different things. So the sign chart must have, or with, x-intercepts, vertical asymptotes, and holes. Okay? So all three of those have to be included. Now again, we're rarely going to see the holes. Mostly it's going to be x-intercepts and vertical asymptotes. The rest of this is going to be exactly the same as it was for polynomials. Once you've established where those cutoffs can be, then you plug in x values within each of the intervals, determine the sign for the outputs in those intervals, and then that can tell you what the solution is. Okay? So that's just kind of an overview of how we're going to solve rational inequalities. Now let's take a look at a quick example. Let's take the rational inequality x plus 6 over x minus 2, for instance. I don't know, making this up as I go here. And I need that's only the rational function. I need another part to this inequality. Let's say it's less than or equal to 0. Okay, fair enough. So now what I want to do is find the zeros of this rational function. That'll tell me these three different pieces of information, then I make my sign chart and go on from there. So first of all, the zeros. So I take the top, set it equal to 0. I know the 0 of the top is -6. I take the bottom, set it equal to 0, and I know that is 2. Okay, so -6 and 2 are my zeros. What do they represent? The one from the top represents an x-intercept. The one from the bottom represents a vertical asymptote. And because there's no shared zero between the two, the top and the bottom, I know there are no holes. Okay, so there are no holes. So just kind of keep that aside. Most of your problems will have no holes in them. Okay, so now I'm going to separate my interval using a sign chart. I'm going to have these two values, -6 and 2. Now if I have an x-intercept, that means I'm going to include that point when we have an equal sign, right? Just like we did with polynomials. So if you have an equal sign and an x-intercept, that point can be included. Vertical asymptotes are never included, okay? Never included. Same with holes. Okay? Neither of those are actually included because they're not in the domain of the function. You can't plug them in and get out 0 or get out anything for that matter. Okay, so they're not included. And so for that reason, I'm going to put a dashed line there. Kind of looks like our vertical asymptotes anyway, right? When we graph these things. And so there I know that my 2 is always going to have a parenthesis on it in my interval. Whereas the -6 will have a bracket so long as I have an equal sign here. If I didn't have the equal sign here, then they'd both be parentheses anyway. All right, so now I plug in values to those three intervals. I don't know, let's take -10, that's out here on the left. Let's take 0, that's in the middle, and let's go with maybe 3, that's over there on the right. Again, it doesn't matter as long as it's in the interval. When I plug in a -10, I like to do this just again determining the sign of the top and bottom of the factors. So if I plug in -10 plus 6 is a negative number. In the bottom, -10 minus 2, that's also negative. The negative rules out on both of those. Well, a negative over a negative is positive. And so my sign chart will have all positive values as outputs in that first interval. If I plug in 0, 0 plus 6, that's a positive number. The 6 is greater. And 0 minus 2, well, that's going to be negative because the 2 is greater, okay? When I divide those out, the ratio of a positive over a negative is negative. And that means every output in that interval is going to be negative. Let's go over to 3. Plug in a 3. 3 plus 6, well, that's positive 9. 3 minus 2, well, that's also positive, right? The 3 is bigger. And a positive over a positive is positive. So I have all positive values on the right as outputs. And so now I can determine my final solution simply by looking at these three intervals and determining where my rational function is negative, right, less than 0. Well, it's going to be in this middle interval. Because of the equal sign, I need a bracket on the -6. And because of the asymptote at 2, I know that no matter what, I'm going to use a parenthesis there. And so my interval, my final solution, will be all numbers between -6 and 2, including the -6.